First, we have 3 long papers in this session. The first speaker is Flavian Vasile from Criteo. And his presentation will be on Meta-Prod2Vec, so product embedding with the side information. So thank you.
Thank you, guys. Today I'm going to talk about Meta-Prod2Vec, a way to do simple product embeddings with side information. This is joint work with Elena Smirnova at Criteo and Alexi Kono, who was my intern and is now at FAIR. So let's go over the structure of the talk. I will go very fast over why do we do product embeddings for recommendation, why do we think it's a good idea. Cover the kind of the relevant prerequisites, Word2Vec and Pro2Vec, which is the method we're extending. Then propose our method and show how it works, and then finish with the experimental results and draw some conclusions. So let's get started. So product embeddings for recommendation. As at the beginning of the conference, I think the chair was covering the change in tags for the papers, and he was saying like last year there was no paper on deep learning. And this year, there are plenty, as we saw. Like, why is this a good idea? Like, why do we want to do product embeddings? Actually, at the core, we do what we used to do even before. We represent items and possibly users in a same space, and then we compute their distance. And this way, we get recommendations. So at a certain level, this is nothing new. We had matrix factorization techniques before. So this is just yet another way to do it. As recent papers shown, some of these methods, if you really look deep down at them, they can be mapped back to standard monetization techniques, but then with a couple of tweaks. So either new ways to compute the matrix entries or new loss functions. So at the core, in some sense, there is not much new. It's something that we have been doing for a while. So where do we fit in terms of a landscape of the papers? We are proposing a hybrid model that uses collaborative filtering as the main source of information, and we use the content, product content as side information. So as far as we see, this is one of the first incursions of this kind. So let's go over the related work. So I'm going to go fast through Word2Vec. A lot of people should be familiar by now with the algorithm. I like this image because it kind of, again, makes the relationship with matrix factorization. So what really Word2Vec tries to do is to fit locally embeddings for words in a sequence. So in the skipgram model, it uses the center word in the window as the context of the other words, and it tries to model the conditional probability of the surrounding words as a softmax over 2 matrices, an input matrix that maps the vocabulary space to a hidden space, times the output matrix that maps back to the vocabulary space. And then really what you do is trying to do maximum likelihood. So this is what Word2Vec is, really. And the skipgram with negative sampling, it's usually the most used flavor of it. So why is this relevant to recommendation? Well, like in the very beginning, like the first papers on Word2Vec, looked at the resulting representations and tried to see, like what do they do? And what we think it's interesting for product recommendation is the fact that when you do the cosine similarity in this new space, for example, for the word France, the closest words are actually other European countries. For Jesus, other gods. For Xbox, other types of consoles. So it seems to be a reasonable representation for similarity, for semantic similarity. So then very, very fast, people caught on, and they realized that they can do the same trick on different types of sequences. For example, product shopping sequences. So here you have a view of a product, a view of a second product, and a sale of a third product. So now you can do the same type of model where you have the center product trying to explain the context products. And these are in the original paper by Grbovic and others, Dabdala 2013. They did this on email receipts. So they take the Yahoo mails with that are receipts and sort by timestamp and create product sequences. And they call this Pro2Vec. So this is the method we're trying to improve. And what happens is once you have this these embeddings, you can compute cosine similarities or Euclidean distance, and you're supposed to get semantically similar products that kind of have the same function from the point of view of the user sequence, very close. So, and use that for recommendation. As a loss function, what Pro2Vec does, you can derive the fact that it's actually doing the weighted cross entropy between the empirical conditional distribution of the next product given previous product and the softmax representation. So this is a good way to look at what Pro2Vec and RecSys do for us to motivate and to develop an intuition for Meta-Prod2Vec, as we will see soon. So now let's go over our method. So the main idea is why should we throw away the product metadata when we do the product embeddings? Like we have the product sequence, so we're just looking at the IDs and their co-occurrences, but can we do something with the metadata? And where could that be useful? Well, first of all, we should look at co-star because the sequence information there will be sparse. Like some products will never co-occur, but there are other things about them that appear in the metadata that could prove useful to regularize. So this is exactly the thing we will try to do is to place additional constraints on the product embeddings, the product embeddings that like model co-occurrences using the external information. And this way we can create more noise robust embeddings for the products suffering from cold start, like in areas with low counts. And the type of product side information that we could use, it's mostly discrete features. Like we only looked at discrete features, so things like categories, brands, title, description, tags. And most of these things, I mean, any of these things will have more generalization power than the ID, the product ID, because most of the properties of the product appear over multiple products. So they'll have better support in the data. So let's see how our method leverages this extra information. So we're going to do a motivating example. So let's say we try to do a very simple recommender system for songs. And the solution is really look at the last song that the user listened and try to recommend the next song. So that places us in a very simple setup where we do an item-to-item recommendation. And this very simple solution will have two situations when trying to do recommendations. It will have the simple case where the previous song, the query song, is popular, and then basically it will have good support in the data to see, what is this song similar with from the point of view of collaborative filtering, and the hard case where the previous song will have relatively low volume, so it will suffer from cold start. So let's look at the simple case. Let's say that we listen to Shake It Off by Taylor Swift, and then in the data, just by simple collaborative filtering, like a neighborhood method, you can find out that, let's say, it's all about the bass by Meghan Trainor. And I use the YouTube best suggestion for that. So in this case, both collaborative filtering and Pro2Vec should work. I mean, it's an easy case. But now let's say that we have the same artist, still Taylor Swift, but then now it's an early song, and it doesn't have that much support in the data. And maybe it does, actually, because she's so popular. But for the point of argument, let's say that she's not. Now it's a hard choice. What do we do with the next song? And let's say we not only have the problem that we have sparsity on this song, we just also get unlucky. We have the fact that the only observation we have in the training set is that there is this one user that listened to the song and for some reason also listened to Rammstein, and he listened to Du Hast. So for those who know, these are not very frequent occurrences, but it can happen, right? So when you're gonna try to model your recommendation based on co-occurrences, the only thing that you can recommend is Rammstein. And obviously for most of your users, the recommendation looks like it's not working, except for that guy. So this is where we think taking account the meta information, it's a good thing. So now we narrow down on the type of metadata we want to do, and in this case it's the song artist, which is very very intuitively appealing, and we try to see how we can put additional constraints on our optimization using it. So again, as we saw in the formula, what we're trying to do with Pro2Vec is to model the probability of seeing Du Hast after you saw You're Not Sorry. And what we're facing is the fact that this has low support. So because the song is a fringe song, the co-occurrences will be low. And in this case, it's 1. But yeah, how much should we trust that? On the other hand, the artists are a lot more popular. So even if this song is not popular, Taylor Swift herself is very popular. And we can learn from previous sequences that the co-occurrences of Taylor Swift and Rammstein just are very rare. So the conditional probability of Rammstein given Taylor Swift is really small. And therefore, also the vectors of these two guys now will be, their embeddings will be very distant in the new space. So you know already that Taylor Swift is very far from Rammstein in the embedding space. Furthermore, it's obvious that the songs by Taylor Swift should be close to their artist, and same thing for Du Hast and Rammstein. So now you basically put a constraint on how far can your not sorry be from Taylor Swift and Du Hast from Rammstein, and through basically metrics, through the property of being a metric, then you have that your not sorry and Du Hast are very likely to be pretty far. And we add two more constraints, which even if they're not so intuitively appealing, they still have more support in the data than the original song pair. The off-diagonal ones, the diagonal ones, basically the previous artist for the next song transition and the previous song to next artist. And we tested through experiments that these relations are actually valuable, and we found that they add extra information. So to recap, these are the four constraints we added to the model, on top of the original one, which is just the black arrow. So to formalize this, the derived loss for Meta-Prod2Vec, it's the original loss, which is trying to explain only the sequence, the song sequence, plus a hyperparameter that represents how interested are we in modeling the four other constraints, which are the ones that model the interaction of the songs with their metadata. And to go back a bit to matrix factorization, you can see this as being an augmented matrix where this is the original co-occurrence, song co-occurrence, and now you add this other views with the category, with the artist in this case. And this is the identity matrix. So what's simple about Meta-Prod2Vec, as I promised it's going to be simple. The code doesn't change, so the optimization code is the same, so you can just use Prod2Vec as it is. The only thing you need to do is change your generator for the input pairs. So now we can generate not only the song pairs, but also the four other types of pairs proportionate to the importance of the hyperparameter. So this way you help these vectors to be better regularized. So now let's go over the experimental results. So we chose the task of next event prediction, which is becoming, I guess, more popular these days, and metrics, ranking metrics, hit ratio at K, and NDCG. So as a set of competing methods, we chose just to rank by popularity. We call this best of, a baseline model, like a neighborhood model that does cosine similarity of the candidate items to the query item, Prod2Vec, Meta-Prod2Vec, and then two ensemble methods that very simple linear combination of the two scores. And the data set that we use, we chose the 30 music data set, which is generated from playlist data from Last.fm API, and we use 100,000 sample of user sessions. And they're quite big, as you can see. There are a lot of songs and a lot of artists. So in terms of global results, we divide the methods in like 3 classes, like by our expectation to perform. We expect that popularity and co-counts, basically neighborhood method, standard CF, should work on popular items, what we call the head of the distribution. The embedding method should work better on tail, and then the mix, we want it to basically work on the whole distribution. So this is confirmed by the results. So we see that out of all of these methods, we see best of doing pretty much the worst, which is normal. Co-counts being quite competitive and actually beating the embedding models by itself. But then we see that Meta-Prod2Vec adds a lot more value to the co-count method than Prod2Vec, and becomes the best model in both NDCG and hit rate. And now to narrow down on the cold start, where we are the most interested, we look at the results where the test pair was never seen in the training. So that basically is link prediction. So pair frequency 0 means that you never saw this pair of query next item in training, and then this is you saw it once or twice. So of course, co-counts has no chance to do anything because you never seen this pair. Best of does pretty well. Pro2Vec does slightly better, and then Meta-Prod2Vec does much better. And then when pair frequency is low but non-zero, the mix already is doing much better than all the other methods. So now let's conclude. So obviously, what we see is that using side info for product embeddings helps, and especially on cold start. So what do we want to do next? As the guys at Google with the deep and wide, we are trying to see how to mix the two predictors on like head traffic and the tail traffic to create a better global estimator. So when do you choose the two? Like, is it just this is the best to just blend the two scores? We believe probably not. And then also something that probably I didn't insist maybe enough on it. Right now we're really throwing away the artist vector at the validation time, at the scoring time. You're still using only the song, but it's regularized by the artist embedding, as we saw in the example. So we think that we can leverage also test time. So what we're working on is to have like a global, like a holistic product embedding that uses all the available signal for the product. So collaborative filtering and anything that means content. So categorical features and text and image. So that's our next project. With this, thank you, and I'm open to questions. Thank you.
So, thanks, Flavian, for the presentation. Are there any questions?
Hey, I have a question about the early part of your presentation. About the choice of similarity metric. All of these embedding methods, eventually when you come up with embedding vectors, recommendations involve doing a nearest neighbor search according to some similarity metric. And you mentioned cosine similarity. The problem I have with that is that unless you somehow make sure that your vectors turn out to be normalized, when you're using cosine similarity, you're basically throwing in information that is encoded in the norm of these vectors. So it seems like an Euclidean distance is a better similarity metric compared to cosine similarity. Yeah, like I said, unless you make sure that your vectors are normalized, which in the case of matrix factorization is not generally the case.
Yeah, there is no guarantee on being normalized. Indeed.
Thoughts on that?
So we only tried inner product and cosine. Euclidean could be something that we could try. We were surprised to see that actually cosine works much better than inner product, because in the end you use the inner product to fit your model. Yeah, we're trying to understand exactly why are we seeing this like pretty good lift in metrics for ranking. But as you said, yeah, Euclidean could be something to look at.
Okay, I think we have time for another question. There.
Hi, thank you for your presentation. I have a quick question. It looks like that in the end, this mixed model, the hybrid model, is the best model, right? Yeah. The learning of this, the thing that I didn't understand is that, is this part of your learning or no? You just make two models and then just try to make another linear model.
Set we just do line search and find the best alpha. So it's not part of like it's.
Oh, it's not part of your network.
It's not part of we don't backprop straight or anything.
All right, I see. Thank you.
Okay, so if there are other questions, I suggest you to discuss with the speaker at the end of the session. So thank you again. The next.